Every single thing you have ever seen began in one fleeting moment. We are going on a journey through 30 of the most profound questions about the universe, from its fiery birth to its mysterious end. You will gain a new understanding of the cosmos, from the tiniest particles to the vast, dark energy pushing everything apart. We will uncover why the universe is made of matter and not antimatter, and what might have existed before time itself began. What single cosmic mystery keeps you up at night? That single moment of creation, the Big Bang, is the starting point for our entire cosmic story. But what was it really? The name itself is a little misleading. We often picture a giant explosion, a fireball erupting into an empty, black void. But the reality is far stranger. The Big Bang was not an explosion in space. It was the sudden, rapid expansion of space itself, everywhere at once. Imagine the entire universe, all the energy and matter that would ever exist, compressed into a point of unimaginable heat and density. Then, in an instant, space began to swell, carrying that nascent energy with it. Think of a loaf of raisin bread dough before it bakes. As the dough expands in the oven, every single raisin moves away from every other raisin. No raisin is the center. The expansion is happening throughout the entire loaf. Our universe is like that rising dough, with galaxies as the raisins, all drifting apart as the fabric of space itself stretches. We are not just guessing at this. The evidence for this incredible event is written across the sky. The first major clue is the cosmic microwave background radiation. This is the faint, leftover heat from the Big Bang, a cosmic echo that fills every direction of space. It is the cooled remnant of that initial fireball, now just a few degrees above absolute zero, and it serves as a snapshot of the universe when it was only 380,000 years old. The second key piece of evidence is the redshift we see from distant galaxies. As space expands, it stretches the light traveling through it, shifting its color toward the red end of the spectrum. The farther away a galaxy is, the faster it appears to be receding from us. This tells us the universe is not static, it is still growing. So we have a solid framework for what happened, but the deepest mysteries remain. We do not know what banged. We do not know what triggered that initial expansion from a state of infinite density, a point scientists call a singularity. The laws of physics, as we understand them, simply break down at that moment. This is the very edge of our knowledge, the precipice from which our 30 questions will leap into the great unknown. This precipice of knowledge forces us to ask one of the most disorienting questions of all. What existed before the Big Bang? Our instincts demand an answer. We are wired to think in terms of cause and effect, a sequence of events where something must always come before. But here, our intuition may be leading us astray. If the Big Bang marked the beginning of space and time as we know them, then the very idea of a before becomes meaningless. Asking what came before the Big Bang might be like asking what is north of the North Pole. The question itself, framed in the language of time, might not apply to a reality where time did not yet exist. Scientists and philosophers have not surrendered to this logical puzzle, however. They have proposed several breathtaking theories that attempt to peer beyond that initial moment. One compelling idea is the cyclical universe model. In this view, our universe is just one in an endless series of cosmic cycles. It expands from a Big Bang, evolves for billions of years, and then eventually contracts back down in a big crunch, only to be reborn in another Big Bang. In this scenario, there is no true beginning or end, just an eternal, rhythmic dance of creation and destruction. Our entire cosmic history would be a single breath in an infinite cosmic lifetime. Another radical proposal is the multiverse hypothesis. This suggests our Big Bang was not a unique event, but merely one bubble inflating in a vast, eternal cosmic foam. In this wider multiverse, new universes are constantly popping into existence, each with its own distinct laws of physics. Our universe simply happens to be one where the conditions are just right for stars, planets, and life to form. Before our universe, there was just this bubbling, frothing quantum sea of potential from which our cosmic bubble spontaneously emerged. Then there is the concept of a quantum fluctuation from nothing. In the bizarre world of quantum mechanics, empty space is not truly empty. Particles and energy flicker in and out of existence all the time. Some theories suggest our entire universe could be the result of a massive, stable quantum fluctuation, a bubble of space-time that simply popped into being from a state of nothingness and then inflated to become everything we see. The truth is, we simply do not know. This remains one of the ultimate frontiers of human understanding. The question of what, if anything, preceded our universe challenges the very foundations of our reality, forcing us to confront the profound nature of time and existence itself. It is a mystery that may forever lie just beyond our grasp, a silent, timeless enigma waiting at the origin of all things. That silent enigma at the origin of everything is followed by another, even more dramatic event. The universe, in its first fleeting fraction of a second, did not just expand. It exploded outward at a speed that defies all intuition. This is the theory of cosmic inflation, a period of exponentially rapid expansion that took the newborn cosmos from smaller than a proton to a vast, macroscopic size in less than a blink of an eye. This was not the steady, stately expansion we see today, but a monstrous growth spurt that solved some of the Big Bang's deepest puzzles. Take the horizon problem. Look at the cosmic microwave background, the oldest light in the universe. No matter which direction you point your telescope, this afterglow has almost exactly the same temperature. But how can two opposite sides of the sky be so perfectly in sync? In the standard Big Bang model, there simply has not been enough time since the beginning for light or heat to travel from one side to the other to even out the temperature. They are like two people stranded on distant islands with no way to communicate, yet they are both wearing identical clothes. It makes no sense unless those two islands were once part of the same tiny landmass. Inflation solves this. It proposes that the entire observable universe was once a microscopic, interconnected region that was heated to a uniform temperature before inflation violently stretched it to the colossal size we see today. The regions that now appear impossibly distant were once neighbors, close enough to share their heat. Then there is the flatness problem. Measurements show the large-scale geometry of our universe is incredibly flat, like a perfectly stretched sheet. This is a very precarious balance. For the universe to remain this flat for over 13 billion years, its initial density at the Big Bang had to be fine-tuned to an astonishing degree of precision. The slightest deviation would have caused the cosmos to either collapse back on itself immediately or fly apart so fast that no stars or galaxies could ever form. Such perfect initial conditions seem wildly improbable. Inflation makes this fine-tuning natural. Think of blowing up a balloon. No matter how wrinkled or curved its surface was when it started, as you inflate it to an enormous size, any small patch of its surface will appear increasingly flat. The violent stretching of space during inflation did the same thing to the entire cosmos, ironing out any initial curvature and leaving us with the flat universe we observe. So what could have powered this incredible burst of expansion? Physicists propose a hypothetical energy field called the inflaton field that permeated the early universe. Think of it like a cosmic engine stuck in a high-energy state that generated a powerful repulsive force, causing space to stretch at an unimaginable rate. But this field was unstable. After that tiny fraction of a second, this inflaton field decayed, releasing its pent-up energy in a torrent that flooded the universe, reheating it into the hot soup of particles we recognize from the standard Big Bang. And in that moment of decay, something miraculous happened. Tiny quantum fluctuations, the microscopic jitters inherent to all fields, were stretched to astronomical sizes by the rapid inflation. These minute ripples in the fabric of space-time became the gravitational seeds for all future structure. They were the slight over densities, the places where just a little bit more matter began to gather, that would later, over billions of years, collapse under their own gravity to form the very first galaxies, stars, and eventually us. Every galaxy cluster, every swirling spiral, and every solitary star exists because of those quantum whispers, magnified by inflation into the grand architecture of the cosmos. Those quantum whispers set the stage, but the universe was still a searing, featureless ocean of pure energy. In this primordial fire, the very laws of physics were simpler, and the forces that govern our reality were one. We recognize four fundamental forces today: gravity, the architect of planets and galaxies; electromagnetism, which binds atoms and gives us light; the strong nuclear force, which glues atomic nuclei together; and the weak nuclear force, which drives radioactive decay. But in the first unimaginable moments after the Big Bang, these four were almost certainly a single, unified superforce. Think of water. At a high temperature, it is a single, uniform substance, but as it cools, it can undergo a phase transition, freezing into solid ice. In a similar way, as the newborn universe expanded and cooled, the single unified force is thought to have undergone its own cosmic phase transitions, freezing out into the distinct forces we now measure. The first force to peel away was gravity. Why gravity separated first remains one of the deepest mysteries, as we still struggle to reconcile it with quantum mechanics. Then, as the universe continued to cool in that first fleeting fraction of a second, the strong nuclear force split off from the electroweak force. Finally, a little later, the electroweak force itself broke apart, giving us the distinct electromagnetic and weak nuclear forces we see today. This cosmic winnowing left us with the four separate forces that structure our world. The dream of modern physics is to reverse this process, to find the mathematical key that can merge these forces back together. This is the quest for a grand unified theory, or GUT. The goal is to show that the electromagnetic, strong, and weak nuclear forces are just different facets of a single underlying force. It would be a monumental achievement, revealing a hidden simplicity beneath the apparent complexity of nature. So why is this so difficult to prove? The energies required to see this unification are staggering. To smash particles together with enough force to make the electromagnetic and strong force reveal their shared identity, we would need a particle accelerator larger than our entire solar system. It is a scale we cannot possibly reach in any laboratory. Instead, physicists look for subtle, indirect clues. They search for rare particle decays predicted by these theories, or they study the conditions of the early universe itself, using the cosmos as its own ultimate laboratory. The greatest challenge, however, remains gravity. A grand unified theory does not include it. The ultimate prize is a theory of everything, a single elegant framework that encompasses all four forces, including gravity. Finding it would be like hearing the original, unified note from which the entire symphony of the cosmos was composed. This cosmic symphony of forces is conducted by a set of unbreakable rules, the laws of physics. But who wrote the rule book? The speed of light, the strength of gravity, the mass of an electron? These are not just numbers. They are fundamental constants, and they appear to be exquisitely fine-tuned. Change them by even a tiny amount, and the universe as we know it would vanish. If gravity were slightly stronger, the universe would have collapsed back on itself long before stars could form. If it were slightly weaker, matter would have flown apart too quickly to ever coalesce into galaxies. The nuclear forces that bind atoms are also perfectly balanced. If the strong force were just a bit more powerful, all the hydrogen in the early universe would have fused into helium, leaving no fuel for stars like our Sun. If it were weaker, no complex atoms could ever form. There would be no carbon, no oxygen, and no chemistry for life. This incredible precision is known as the fine-tuning problem, and it demands an explanation. One provocative answer is the anthropic principle. In its simplest form, it states that we observe these particular constants because they are the only ones that allow for our existence. We are, in a sense, selecting for a universe that can produce us. The universe is not fine-tuned for life. Life is just a possible outcome in a universe tuned this way. It sounds almost like a truism, but it forces a profound shift in perspective. We are not the intended purpose of the cosmos, but rather a fortunate byproduct of its specific rules. This line of thinking naturally leads to more radical possibilities. If the constants seem improbably perfect, perhaps there is not just one universe, but a vast multiverse. In this cosmic landscape, countless other universes are constantly bubbling into existence, each with its own random set of physical laws and constants. In most of these universes, the numbers are all wrong. They collapse instantly, or they are barren, empty voids with no structure at all. We, of course, can only exist in one of the rare Goldilocks universes where the numbers are just right for complexity and life. Our universe is not special, it is just lucky. An even more mind-bending proposal is the simulation hypothesis. What if our universe, with its seemingly arbitrary but perfectly set constants, is not fundamental at all? What if it is an incredibly advanced computational construct, a simulation running on some unfathomable computer built by a super-intelligent civilization? In this scenario, the laws of physics are simply the underlying code of the program, and the constants are the parameters chosen by the programmer. While this idea often feels like science fiction, some philosophers and physicists take it seriously as a logical possibility, one that could potentially explain the mathematical nature of our reality. Ultimately, the origin of physics itself remains the deepest of all mysteries. Are these laws truly fundamental, eternal truths that exist independently of the universe? Or did they themselves emerge from something else during the Big Bang, perhaps crystallizing from a more primal, lawless state? We do not know if we will ever find an answer, but the search forces us to confront the very nature of reality, questioning whether the rules we take for granted are the only ones possible, or merely the local bylaws of our own cosmic neighborhood. Those perfectly balanced laws of physics, however, describe only a tiny fraction of what actually fills the cosmos. All the stars, galaxies, and planets we can see are built from ordinary matter, the protons, neutrons, and electrons that make up everything from you to the most distant quasar. Yet this familiar stuff accounts for less than 5% of the universe. The rest is a complete mystery, dominated by two unknown entities we call dark matter and dark energy. Let us focus on the first, the invisible scaffold of the cosmos. Dark matter is a substance that does not emit, absorb, or reflect any light. It is completely transparent, utterly invisible to our telescopes. So how can we possibly know it is there, let alone claim it makes up 27% of everything? We see its ghostly gravitational hand at work. In the 1930s, astronomer Fritz Zwicky was studying a giant cluster of galaxies. He noticed that the individual galaxies were moving so fast that the cluster's gravity, based on the visible matter alone, should not have been able to hold them together. The entire cluster should have flown apart. The only explanation was that there was far more mass there than anyone could see, a hidden source of gravity binding the cluster together. We see this same effect on smaller scales within individual galaxies. Stars at the outer edges of spiral galaxies orbit at speeds that defy logic. If a galaxy's gravity came only from its glowing center of stars, these outer stars should be moving much more slowly, like planets in our solar system that orbit more sedately the farther they are from the Sun. But they are not. They whip around at nearly the same high speed as stars closer in. It is as if each galaxy is embedded within a vast, massive sphere of something invisible, a dark halo whose immense gravity is what truly dictates the motions of the stars. This dark matter is not just a passive ingredient, it was the master architect of the cosmic structures we see today. After the Big Bang, the universe was a nearly smooth soup of particles. But dark matter, being unaffected by the intense light and radiation that buffeted ordinary matter, was able to start clumping together first. It formed a vast, invisible web of gravitational wells across the cosmos. Ordinary matter, the hydrogen and helium gas, was then pulled into these pre-existing dark matter scaffolds. Without this gravitational framework, the gentle tugs of ordinary matter alone would not have been strong enough to overcome the universe's rapid expansion. There would have been no grand gathering of gas, no collapse into the first stars and galaxies. We owe our very existence to this unseen cosmic architecture. So what is it made of? The leading candidate is a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, and as their name suggests, they would interact with ordinary matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. For decades, scientists have been trying to catch one. Deep underground, in abandoned mines and beneath mountains, detectors are shielded from cosmic rays, waiting for the rare, telltale bump of a dark matter particle colliding with an atom of ordinary matter. Other experiments look for indirect signals, like the unique particles that might be produced if two dark matter particles annihilate each other in space. So far, the detectors have remained silent. Dark matter continues to be the universe's most pervasive ghost, its gravitational presence undeniable, yet its fundamental nature one of the most profound and elusive secrets in all of science. Yet for all its power to shape the cosmos, dark matter cannot account for the universe's most bizarre behavior. An even deeper mystery emerged at the end of the 20th century, one that revealed the cosmos is not just expanding, but its expansion is speeding up. This discovery was so shocking it earned the Nobel Prize. Two independent teams of astronomers were measuring the distances to extremely far-off supernova, using these exploding stars as cosmic mile markers. They expected to find that the expansion of the universe was slowing down as the collective gravity of all matter pulls everything back together. It was like tossing a ball into the air, expecting it to slow, stop, and fall back to Earth. But their data revealed the opposite. The distant supernovae were fainter than they should have been, meaning they were farther away. The universe's expansion was accelerating. The ball was not falling back, it was shooting skyward faster and faster. This was the signature of a completely unknown force, one that overwhelms gravity on the largest scales. Scientists named it dark energy. This mysterious component now makes up a staggering 68% of the entire universe. It is the dominant force shaping our cosmic destiny. So what are its properties? Unlike matter or dark matter, which clump together under gravity, dark energy appears to be a property of space itself. It has a repulsive effect, a kind of cosmic anti-gravity that pushes the fabric of the universe apart. The more space there is, the more of this repulsive energy exists, leading to a runaway effect where the expansion perpetually accelerates. The simplest explanation is Einstein's cosmological constant, a term he originally inserted into his equations to force a static universe, which he later called his greatest blunder. He did not know about the expanding universe at the time, but his constant perfectly describes a uniform energy density inherent to the vacuum of space. In this view, dark energy is the constant, unchanging cost of having empty space. The energy of nothingness is not zero, but it might not be that simple. Another possibility is that dark energy is a dynamic force field, nicknamed quintessence, which could change over time. Unlike the static cosmological constant, quintessence could fluctuate, growing stronger or weaker as the cosmos evolves. This would open up wildly different futures for the universe. The nature of dark energy directly dictates our ultimate fate. If it is a true cosmological constant, the acceleration will continue forever. Galaxies will be pulled apart from one another, their light eventually fading from view as space stretches faster than light can cross it. The universe will end in a cold, dark, and lonely isolation. If dark energy is quintessence, the possibilities are even more dramatic. It could eventually reverse, causing a big crunch that collapses the universe. Or it could strengthen catastrophically, leading to a big rip where the repulsive force becomes so powerful it tears apart galaxies, stars, planets, and even atoms themselves in a final, violent instant. We simply do not know. Dark energy is the central question for cosmology today, the invisible hand that is writing the final chapter of our cosmic story, and we are only just beginning to read the words. The same dark energy that pushes galaxies apart was born from a universe that was once too hot for even atoms to exist. For the first few microseconds, the cosmos was a searing, opaque soup of fundamental ingredients. This was the quark-gluon plasma, a state of matter so extreme that the quarks and gluons that normally make up protons and neutrons were utterly unbound, zipping around freely in a dense, chaotic frenzy. It was a world without structure, a primordial sea of pure potential. Then, as the universe expanded and cooled past a critical threshold, a cosmic freeze-out occurred. Think of it like water vapor condensing into droplets. The quarks, suddenly feeling the powerful grip of the strong nuclear force, were snared into groups of three, locking together to form the first protons and neutrons. In less than a blink, the building blocks of atomic nuclei were born from the cooling embers of the fireball. But these particles were alone in a raging sea of radiation. For nearly 4 minutes, the universe remained too hot and dense for these fledgling protons and neutrons to stick together. Any attempt to form a nucleus was immediately blasted apart by a photon with the energy of a cosmic sledgehammer. Then the temperature dropped just enough. The universe cooled to around 1 billion degrees, and in a window of opportunity that lasted only a few precious minutes, the first atomic nuclei were forged. This brief, violent period is known as Big Bang nucleosynthesis. Protons and neutrons began to collide and fuse. A proton and a neutron could stick together to form a deuterium nucleus, a heavy isotope of hydrogen. These deuterium nuclei then collided with more protons and neutrons, building up the first helium nuclei. It was a frantic, universe-wide cooking show with the entire cosmos as the kitchen. When the smoke cleared after those few minutes, the universe had expanded and cooled so much that fusion could no longer occur. The result was a cosmic composition of about 75% hydrogen and 25% helium by mass, with only the tiniest trace amounts of lithium. Every other element in the periodic table was entirely absent. Why did the cosmic kitchen close so quickly? The universe was expanding far too rapidly. For a nucleus to grow, it needs to be in a dense, hot environment where particles are constantly smashing into each other. But as space stretched, the density of matter plummeted. The particles were simply too spread out, and their collisions became too infrequent to build anything heavier. There was no way to fuse helium into carbon or oxygen. The universe had created the raw fuel, a vast cloud of hydrogen and helium gas, but it was utterly incapable of forging the complex atoms necessary for planets or life. The stage was now set. The universe was primed, waiting in the dark for the true cosmic forges to ignite, the first stars that would take this simple fuel and transform it into the elements of everything we know. For nearly 400,000 years, the universe remained a searing, opaque fog. Light could not travel freely. Photons, the particles of light, were trapped in a constant, violent dance with a dense sea of free-floating electrons. Every time a photon tried to move any distance, it would immediately collide with an electron and be scattered in a new direction. The cosmos was a brilliant, impenetrable glow, like being inside the sun. Then a profound transition occurred, a moment that astronomers call the epoch of recombination. the universe had expanded and cooled to a temperature of around 3,000 degrees. This was cool enough, finally, for the frantic electrons to be captured by atomic nuclei. The positively charged nuclei and the negatively charged electrons combined to form the first stable, neutral atoms, primarily hydrogen and helium. In an instant, the fog lifted. With the electrons now bound securely inside atoms, the sea of free scatterers simply vanished. The photons, which had been trapped for eons, were suddenly set free. They began to travel across the universe in straight lines, and space became transparent for the very first time. This was the universe's moment of first light. That first flash of liberated light is still all around us today. We detect it as the cosmic microwave background radiation. The expansion of the universe over billions of years has stretched those once visible light photons into the microwave part of the spectrum, cooling them to just a few degrees above absolute zero. This afterglow is the oldest fossil we can ever observe, a baby picture of the cosmos taken when it was a mere 380,000 years old. But this baby picture is not perfectly smooth. It is imprinted with faint, mottled patterns, tiny variations in temperature. Some patches of the sky are ever so slightly warmer, others ever so slightly cooler. These minute fluctuations are the gravitational seeds of our entire cosmic structure. The slightly warmer, denser patches were regions where a little more matter had gathered. Their extra gravity began to pull in even more material from their surroundings. Over hundreds of millions of years, these tiny ripples in the fabric of the early universe would grow, collapsing under their own gravity to form the first stars, the first galaxies, and the vast cosmic web we see today. Every galaxy cluster and every vast, empty void was mapped out in that first brilliant flash of transparency. Those faint temperature variations in the cosmic microwave background are the most important map ever created. They chart the future of everything. But where did these crucial ripples, these slight overdensities and underdensities, originally come from? Their origin lies in the bizarre and tiny world of quantum mechanics, magnified to a cosmic scale. During the inflationary period, when the universe expanded faster than light itself, the very fabric of space-time was not perfectly smooth. At the quantum level, empty space is a seething, bubbling foam. Virtual particles flicker in and out of existence, creating a constant hum of uncertainty. This quantum jitter affected the inflattened field, the very engine driving the expansion. Imagine a vast, smooth sheet being stretched with incredible force. At a microscopic level, the sheet is not perfectly uniform. It has tiny, random wrinkles and bumps. Now inflate that sheet to the size of a continent. Those once invisible imperfections are now enormous hills and valleys. This is precisely what happened during inflation. The infinitesimal quantum fluctuations in the inflattened field were stretched and frozen into the fabric of space-time itself, imprinting the universe with minute differences in density. Some regions had just a little more energy, a little more gravitational pull than others. These ripples are the cosmic blueprints, the gravitational seeds from which every galaxy, star, and planet would eventually grow. Once inflation ended and the universe transitioned to the more sedate expansion of the classic Big Bang, gravity took over. It is the great amplifier of the cosmos. Those regions with a tiny bit more density had slightly stronger gravity. They began to pull in more dark matter, which in turn pulled in more ordinary hydrogen and helium gas. Over hundreds of millions of years, what began as a quantum whisper became a gravitational shout. The slight overdensities collapsed into vast, invisible webs of dark matter, and the ordinary matter flowed into these gravitational wells, igniting into the first stars and coalescing into the first protogalaxies. The entire cosmic web, with its magnificent filaments of galaxies and immense, empty voids, is a direct result of gravity acting on those initial quantum seeds. Without those random fluctuations born from the quantum vacuum, the universe would have remained a cold, dark, and perfectly uniform sea of hydrogen and helium. There would be no clusters of galaxies, no swirling spirals, no solar systems, and no Earth. We are here because the universe began with a pattern of imperfection, a flaw in its initial perfection that allowed for the grand complexity of everything we see. The entire story of cosmic structure is written in those first quantum ripples. For millions of years, the universe was a silent and lightless sea. After the cosmic microwave background faded into the expanding darkness, a profound quiet fell across the cosmos. This was the cosmic dark ages, an era of utter blackness where no stars shone and no galaxies glittered. The universe was filled only with a vast, featureless fog of neutral hydrogen and helium gas slowly cooling in the expanding void. But beneath this apparent stillness, an invisible architecture was taking shape. The dark matter halos, those gravitational seeds amplified from quantum whispers, were steadily growing, pulling in more and more of the unseen mass. These halos acted as cosmic traps, their immense gravity beginning to draw in the primordial gas. Slowly, almost imperceptibly, the hydrogen and helium started to flow into these deep gravitational wells, pooling into gigantic, swirling clouds. These were the proto-galaxies, the nurseries where the first stars would be born. Within these dense, collapsing clouds, pockets of gas began to fragment and condense. Under the relentless crush of its own gravity, a knot of gas would heat up, its pressure rising astronomically as it was squeezed into a smaller and smaller volume. For eons, this was a losing battle, with heat radiating away into space. But eventually, in the core of these collapsing clouds, the temperature reached a staggering 10 million degrees. At this critical threshold, a miracle of physics occurred. The protons, the nuclei of hydrogen atoms, were moving so fast that they overcame their natural electromagnetic repulsion and slammed into one another. In that violent collision, nuclear fusion ignited. The first stars blazed into existence, tearing apart the cosmic darkness forever. These first stars, known as population 3 stars, were unlike anything in the modern universe. They were behemoths, pure and simple, composed only of hydrogen and helium. With no heavier elements to help them cool and fragment, they could grow to incredible sizes, some potentially hundreds of times more massive than our Sun. Their lives were as spectacular as they were brief. Burning their nuclear fuel at a ferocious rate, they lived for only a few million years, a mere heartbeat in cosmic time. But their deaths were even more consequential. These massive stars did not fade quietly. They exploded as supernovae of unimaginable power, blasting their newly forged contents out into the void. In their fiery cores, they had cooked hydrogen and helium into the first heavier elements: carbon, oxygen, nitrogen, and traces of iron. This stardust, the ashes of the first stars, was scattered into the primordial gas, enriching it forever. The universe was no longer pristine. It was now seeded with the raw materials for rocky planets, for water, and for life itself. The dark ages were over, and a new dawn of cosmic complexity had begun. The ashes of those first stars seeded the cosmos with the elements for new worlds, but they also left behind a more ominous legacy. When the most massive of these stellar giants died, they did not just explode. Their cores collapsed into the first generation of black holes, stellar mass predators lurking in the newborn galaxies. Yet this raises a profound puzzle. When we peer back to the universe's first billion years, we see quasars, the intensely bright cores of young galaxies powered by supermassive black holes already weighing billions of times the mass of our Sun. How could something so monstrous grow so quickly from such modest beginnings? It is a cosmic timing problem that challenges our understanding of black hole growth. A stellar mass black hole left over from a supernova should take billions of years to grow to supermassive status by steadily feeding on gas. Yet these cosmic giants were already fully grown in a fraction of that time. One compelling theory is direct collapse. In the early universe, vast clouds of pristine hydrogen gas, untouched by the pollution of heavier elements, could have collapsed under their own immense gravity. But instead of fragmenting into many stars, these clouds may have bypassed starlight entirely, crumpling directly into a massive black hole seed hundreds of thousands of times heavier than our Sun. This gives the black hole a colossal head start, a giant embryo from which it can rapidly balloon into a supermassive titan. Another possibility is a frenzy of mergers. In the dense, crowded centers of the first protogalaxies, many smaller black holes could have formed and then spiraled together, merging over and over to build up mass at a breakneck pace. It would be a chaotic, violent dance in the galactic core, a series of collisions that builds a monster from countless smaller pieces. Once these seeds were in place, whether from direct collapse or mergers, they began to feast. A supermassive black hole is a messy eater. As gas spirals into its gravitational grip, it forms a superheated accretion disk, a maelstrom of matter shining with the brightness of a trillion stars. This is the engine of a quasar, but the black hole's influence extends far beyond its brilliant glow. Some of the infalling matter is channeled by powerful magnetic fields into jets that shoot out from the poles at nearly the speed of light, carving through the surrounding galaxy for thousands of light years. This incredible energy output does more than just illuminate the cosmos. It can regulate the very growth of its host galaxy. These jets and radiation blast away surrounding gas, the raw fuel for star formation. In this way, a supermassive black hole can act as a cosmic thermostat, shutting down star birth and preventing the galaxy from growing too large. It is a dramatic feedback loop where the monster at the center dictates the fate of the entire galactic ecosystem. The existence of these early behemoths suggests that black holes were not just byproducts of galaxy formation, but fundamental architects shaping the evolution of the cosmos from its very infancy. Those supermassive black holes may be the ultimate architects of galaxies, but they too are subject to the universe's final, overarching destiny. The fate of everything hinges on a silent, relentless battle between two opposing forces, the inward pull of gravity and the outward push of dark energy. Right now, dark energy is winning, and its victory will dictate how the cosmos ends. The leading scenario, supported by our current observations, is the Big Freeze, also known as heat death. In this future, the acceleration of the universe continues unabated. Galaxies will be pulled ever farther apart, their light stretching into useless, low-energy radio waves. Existing stars will burn through their fuel and die one by one until no new stars are born. The universe will become a much darker place, populated only by the corpses of stars, black holes, and frozen planets. Even these remnants will not last. Over trillions upon trillions of years, protons, the very building blocks of atoms, may decay, causing all matter to slowly evaporate into radiation. Black holes themselves, through a process called Hawking radiation, will gradually leak their mass away, vanishing in a final faint puff of particles. The universe will approach a state of absolute cold, absolute darkness, and absolute equilibrium, where no energy can be harnessed for any work or any life. It is the ultimate thermodynamic end, a silent, static sea where nothing ever happens again. But is this future certain? The nature of dark energy holds the key to other, more violent possibilities. If dark energy is not a constant but instead grows stronger over time, we could face the Big Rip. In this terrifying scenario, the repulsive force of dark energy would eventually overcome every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the force intensifies, stars would be ripped from their galactic homes. In the final, frantic minutes, the gravitational pull of your own body would be overcome, and you would be pulled apart. In the last instant, planets, molecules, and even atoms would be shredded by the runaway expansion of space itself. The fabric of reality would be torn asunder. There is a third, more cyclical possibility, the Big Crunch. This was once a favored model where the expansion of the universe would eventually slow, halt, and reverse under the collective gravity of all matter. The cosmos would begin to collapse with galaxies rushing toward each other. Temperatures would soar as space is compressed, and the universe would head toward a fiery, singular end, potentially triggering a new Big Bang and starting the cycle all over again. While poetic, this fate now seems unlikely. Our measurements show the expansion is not slowing down, it is speeding up. The data strongly points toward the cold, lonely conclusion of the Big Freeze. This is not a fate that awaits us in any human timescale, but in a cosmic sense, it is the final, quiet whisper of a universe that began in a roar. The story that started with a single, unified force will end, it seems, in infinite, eternal silence. That silent, eternal end forces us to ask a deeply unsettling question. Could our universe, with its specific history and fate, be just one of countless others? This is the radical idea of the multiverse. It is not a single concept, but a collection of theories that all suggest our cosmos is far from unique. One of the strongest arguments for a multiverse comes from cosmic inflation. Recall that brief period of hyper-expansion right after the Big Bang. The theory suggests this inflation is eternal, never truly stopping everywhere at once. In this eternal inflation, new pockets of space-time can continuously bud off, each one undergoing its own Big Bang and evolving into a separate, self-contained universe. Picture a vast, bubbling pot of water. Our entire cosmos is just one bubble that formed and stabilized in that frothing cosmic foam. An infinite number of other bubbles are constantly appearing, each with its own random set of physical properties. This is the inflationary multiverse. String theory, a candidate for a theory of everything, adds another layer. It proposes that the fundamental ingredients of reality are tiny, vibrating strings. But for the math to work, it requires extra spatial dimensions, all curled up into a complex shape. The catch is, there are an astronomical number of possible shapes for these dimensions, perhaps 10 to the 500. Each different shape would result in a different set of physical laws and constants. Our universe, then, would simply be one where the dimensional geometry accidentally produced the right numbers for atoms, stars, and life to exist. This is the string theory landscape, a vast cosmic catalogue of possible realities. Then there is the quantum multiverse, born from the many worlds interpretation of quantum mechanics. In the quantum realm, particles exist in a haze of probability until they are observed. The standard view is that this probability wave collapses into one outcome. But the many worlds interpretation proposes that it never collapses. Instead, the universe splits, branching into multiple copies, each one realizing a different possible outcome. Every choice, every random quantum event spawns new parallel timelines. In one universe, you are listening to this script. In another, you decided to do something else moments ago. This version of the multiverse is an ever-dividing tree of infinite possibilities. So is this real science or just philosophy? The greatest challenge is testability. How can we ever observe another universe if it is forever beyond our cosmic horizon? Scientists are searching for indirect evidence. They are looking for unusual patterns in the cosmic microwave background that might be an imprint from a collision with another bubble universe in the distant past. They are also investigating whether the specific values of our constants might leave a unique signature that points to a wider multiverse. If the multiverse is real, it offers a stunning answer to the fine-tuning problem. Our universe is not miraculously perfect. We just happen to live in one of the rare bubbles where the numbers randomly lined up to allow for our existence. In an infinite multiverse, every possible reality, no matter how strange or barren, exists somewhere. We are not the purpose of creation, but merely a single, fortunate outcome in an endless cosmic lottery. This question of cosmic geometry takes us from the abstract multiverse to the tangible shape of our own home. Is the universe a vast, infinite plane, a colossal sphere, or a twisting, saddle-like surface? The answer depends on the density of all the energy and matter in the cosmos, a critical value that dictates its curvature and its ultimate fate. The possibilities are beautifully simple in concept. A positively curved universe is like the surface of a sphere. On a globe, two travelers starting out on parallel paths, heading due north, for example, will eventually meet at the North Pole. The surface is finite with no edge, and if you traveled far enough in a straight line, you would eventually loop back to your starting point. This is a closed universe. A negatively curved universe has the shape of a saddle or a Pringles chip. On this surface, parallel lines will diverge, spreading apart from each other. This is an open universe, one that is infinite and expands forever. Then there is the perfect balance, a flat universe. Here, parallel lines remain parallel forever. The geometry follows the classic rules we learned in school, and space extends infinitely in all directions. For decades, cosmologists wondered which of these shapes was our reality. The answer came from exquisitely precise measurements of the cosmic microwave background. Those tiny temperature fluctuations we discussed earlier hold the key. Scientists calculated how much the universe should magnify these tiny spots, a process called gravitational lensing, based on its overall geometry. In a strongly curved universe, whether spherical or hyperbolic, the patterns in the microwave background would appear distorted, like looking at a reflection in a funhouse mirror. But the data from satellites like Planck showed something remarkable. The patterns were crisp and clear. The universe on the largest scales we can measure is geometrically flat. This finding has staggering implications. A flat universe strongly suggests that the cosmos is truly infinite. There is no boundary, no center, and no end to the fabric of space. It also tells us that the total density of the universe is precisely balanced at the critical value, a perfect equilibrium between the energy driving expansion and the matter pulling it back. This delicate balance, however, is not permanent. The initial flatness set by inflation is now maintained by the strange dominance of dark energy. The geometry of our universe points toward an infinite expanse and a future that expands forever into an ever-cooling darkness. The survival of our universe hinged on a single, crucial flaw in its original symmetry. For every particle of matter created in the Big Bang's fury, an equal and opposite particle of antimatter should have been born. Think of them as cosmic mirror images, identical in every way but with opposite charge. When a matter particle meets its antimatter twin, they annihilate each other in a flash of pure energy, leaving nothing behind. Given this perfect balance, the entire contents of the early universe should have mutually destructed, resulting in a cosmos filled with nothing but a fading sea of light. The fact that we are here, made of matter, in a universe full of matter, is definitive proof that this symmetry was broken. Somehow, for every billion pairs of matter and antimatter that annihilated, a single, solitary particle of matter was left over. That one in a billion surplus is everything. Every galaxy, every star, every planet, and every one of us is made from that tiny, inexplicable excess. Physicists call this the problem of baryon asymmetry, and solving it requires the early universe to violate three specific conditions, principles that were once thought to be unbreakable. The first is baryon number violation. This means the total number of matter particles, like protons and neutrons, must not be conserved. In our everyday world, you cannot just create or destroy matter. It has to come from or turn into something else. But in the extreme conditions of the early cosmos, the rules might have been different, allowing processes that generated a net matter surplus. The second condition is a violation of both C and CP symmetry. C symmetry, or charge conjugation, means the laws of physics should be the same if you swap every particle with its antiparticle. CP symmetry is more subtle. It means the laws should hold if you simultaneously swap particles for antiparticles and mirror the coordinates, as if looking at the universe in a mirror. If the universe were perfectly C or CP symmetric, matter and antimatter would behave identically, and no excess could ever form. But experiments have shown that certain particles actually behave slightly differently from their antimatter counterparts, a tiny crack in the mirror that could have been amplified in the early universe. The final condition is that these processes had to occur out of thermal equilibrium. If the universe was perfectly uniform and balanced, any matter produced would have just been re-annihilated. There had to be a departure from that equilibrium, a cosmic moment of disruption where the asymmetry could be frozen into place before it was wiped out. The search for the precise mechanism, a process called baryogenesis, is one of the most active frontiers in physics. Scientists are recreating the conditions of the early universe in colossal machines like the Large Hadron Collider at CERN. By smashing particles together at nearly the speed of light, they create a fleeting, microscopic fireball reminiscent of the Big Bang, hoping to catch a glimpse of a new physics that treats matter and antimatter differently. They are studying the behavior of exotic particles like neutrinos, wondering if these ghostly travelers, which barely interact with anything, could hold the secret. Could they be their own antiparticles, and could this unique property have triggered the imbalance? Other theories look to the very first moments after the Big Bang, suggesting that the phase transitions when the fundamental forces separated may have created bubbles in the cosmos where these symmetry-breaking conditions were just right. It is a cosmic detective story where the clue is our own existence. Finding the source of this primordial preference for matter would not just explain why we are here, it would reveal a fundamental lopsidedness woven into the very fabric of reality, a fundamental reason why the universe ultimately chose one path over another. That 1 in a billion surplus of matter gave us the raw atoms, but they were still solitary and adrift. The violent deaths of the first stars had scattered a new, richer blend of elements into the cosmos: carbon, oxygen, silicon, and iron. Yet for chemistry to truly begin, for the universe to build anything more complex, these individual atoms needed to find a way to link hands. The problem was the environment. Interstellar space is incredibly empty and cold, a far cry from the dense, hot cores of stars where atomic nuclei could fuse. How could two atoms ever get close enough and calm enough to form a stable bond? The very first and most crucial molecule to form was molecular hydrogen, or H2, simply two hydrogen atoms bound together. But getting two lone hydrogen atoms to stick is surprisingly difficult. When they collide, they tend to just bounce off each other. They need a third body, a sort of cosmic chaperone, to absorb the excess energy from the collision and allow the bond to stabilize. In the vast, open void, such three-body meetings were incredibly rare. The solution came from the ashes of those first supernova. Mixed in with the gas were microscopic dust grains, solid particles of carbon and silicon compounds. These tiny motes became the universe's first chemical laboratories. A lone hydrogen atom could drift through space and stick to the surface of a dust grain, like a lonely traveler finding a resting place. Then a second hydrogen atom could land right next to it. On the solid, cold surface of the grain, these two atoms could slide around, meet, and link up, with the dust grain itself acting as that essential third body, soaking up the binding energy. Once formed, the new hydrogen molecule could be knocked loose by another particle or by the energy of its own formation, floating free into the galactic cloud. This was a monumental step. Molecular hydrogen is much more efficient at cooling giant clouds of gas than atomic hydrogen. As these clouds cooled, their internal pressure dropped, allowing gravity to overcome it and cause the cloud to collapse further. This more efficient collapse was the key to forming second-generation stars, and more importantly, the dense, cold cocoons around them where planets would eventually coalesce. But hydrogen was just the beginning. With carbon and oxygen now available, more complex molecules could arise. On the surfaces of these same dust grains, atoms of oxygen and carbon met with hydrogen, forging the first molecules of water, H2O, and carbon monoxide, and even simple organic molecules like methane. These microscopic, icy-coated dust grains were the seeds of all future chemistry. They were the primordial building blocks that would later be incorporated into new solar systems, swirling in the protoplanetary disks around young stars. The water in your glass and the carbon in your body can trace their lineage back to these first, fragile molecular bonds formed on specks of stardust in the dark, cold clouds between the stars. This was the universe's quiet and patient shift from a purely physical realm to a chemical one, setting the stage for the immense complexity that was still to come. Those fragile molecular bonds were the first whispers of chemistry, but their very existence depended on a far stranger and more fundamental set of rules. The universe at its smallest scale does not follow the predictable laws that govern planets and stars. It operates on the bizarre principles of quantum mechanics, a realm where probability reigns and particles can be in multiple places at once. This quantum weirdness is not confined to microscopic laboratories. Its fingerprints are etched across the entire cosmos, from the first instant of creation to the largest structures in space. During the inflationary burst, the universe was smaller than a single atom. At that scale, quantum rules were the only rules. The inflattened field, that cosmic engine driving the expansion, was subject to the inherent jitter of the quantum vacuum. Virtual particles flickered in and out of existence, creating tiny, random fluctuations in the field's energy. As inflation violently stretched space, these infinitesimal quantum ripples were magnified to astronomical sizes. They became the slight variations in density, the gravitational seeds that would later guide the formation of every galaxy. The entire cosmic web, with its vast filaments and empty voids, is a quantum pattern writ large across the sky. Another quantum phenomenon, entanglement, suggests an even deeper connectedness. When two particles become entangled, they share a single quantum state. Measuring one instantly influences the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to violate the speed of light. Yet it is a proven feature of reality. Some physicists speculate that in the early, ultra-dense universe, everything was entangled. While this quantum link does not transmit information, it hints at a profound underlying unity, a hidden quantum fabric that may still underpin the cosmos. This leads to the greatest confrontation in all of physics. Quantum mechanics describes the world of the very small with breathtaking accuracy. General relativity describes the force of gravity and the large-scale structure of the universe with equal success. But the two theories are fundamentally incompatible. They speak different mathematical languages and break down under extreme conditions. To understand the universe's true birth, the moment of the Big Bang itself, we need a theory that can marry them. We need a theory of quantum gravity. At the center of a black hole and at the very beginning of time, all the mass and energy of the universe was compressed into an infinitesimal point, a singularity. Here, the quantum world and the world of gravity collide. General relativity predicts the singularity's infinite density, but this is where its equations fail. Quantum mechanics should take over, but we have no complete theory to describe gravity at the quantum level. What was the true nature of that first cosmic seed? Was it a singularity, or did quantum effects prevent such an infinite state, perhaps forming a bouncing loop or a fuzzy quantum cloud? The quest for quantum gravity is the search for the universe's first memory, a glimpse into the moment when reality as we know it first flickered into being. We can trace the universe's birthday with a cosmic clock that ticks backward from today's expansion. The most direct method relies on the Hubble constant, a number that tells us how fast the universe is currently stretching. By carefully measuring the speeds at which distant galaxies are receding from us and their precise distances, astronomers can calculate this expansion rate. Once we know how fast space is stretching now, we can run the film of cosmic history in reverse, imagining all those galaxies flying back toward each other. We rewind the expansion until all matter and energy converge to a single point, a moment of infinite density. The time it takes to rewind to that starting point is the age of the universe, which comes out to approximately 13.8 billion years. But what if our measurement of the Hubble constant is slightly off? This is where independent checks become vital, and the universe provides us with other ancient timekeepers. We can look at the oldest stars we can find, particularly those in globular clusters that orbit our Milky Way. Using our understanding of stellar evolution, we can determine how long these stars have been burning their nuclear fuel. The very oldest of these stars are dated at over 13 billion years, providing a solid lower limit for the cosmos's age. The universe must be older than the stars within it. The most powerful confirmation, however, comes from that baby picture of the universe, the cosmic microwave background. Spacecraft like the Planck satellite have mapped its faint temperature fluctuations with exquisite detail. By analyzing the precise patterns of these hot and cold spots, scientists can deduce the universe's ingredients, the amounts of ordinary matter, and dark energy. This recipe directly tells us how the universe expanded over time. The Planck data, when fed into our cosmological models, independently points to an age of 13.8 billion years. It is a stunning convergence, three completely different lines of evidence: the current expansion rate, the ages of the oldest stars, and the snapshot of the infant universe, all agree on that one profound number. This is not a single guess, but a triple-locked conclusion, giving us remarkable confidence that we have truly uncovered the timeline of our cosmic origins. Our reality is not a static stage, but a dynamic, living fabric. This is the revolutionary idea of space-time, a concept born from Einstein's theory of general relativity that forever changed our understanding of the cosmos. Space-time is the seamless fusion of the three dimensions of space with the one dimension of time into a single, four-dimensional continuum. Think of it not as a rigid grid, but as a vast, flexible sheet like a trampoline. When you place a heavy object on a trampoline, the fabric stretches and curves downward. Now, roll a marble across that warped surface. The marble will not travel in a straight line. It will spiral inward, following the curve created by the heavy mass. This is not because the marble is being pulled by a mysterious force, but because it is simply following the shortest path along the curved geometry of the fabric. This is gravity. The Sun, a massive object, creates a deep well in the space-time fabric. Earth and all the planets are like marbles following the curved paths, the orbits around that indentation. We are not being pulled by an invisible string. We are simply cruising along the contours of warped space-time. This geometric view of gravity was a monumental leap, explaining everything from the orbit of Mercury to the bending of starlight. But this leads to a more profound implication for the beginning of everything. The Big Bang was not an explosion of matter into a pre-existing empty space. It was the explosive birth of spacetime itself. Before that moment, there was no space to expand into and no time for events to unfold within. The universe did not appear in a location. It was the location beginning to exist and expand all at once. So, what does it mean for spacetime to expand? We are not talking about the fabric stretching into some larger external void. Instead, think of the fabric itself generating new space between every point. It is like the surface of an inflating balloon. As you blow it up, every point on the balloon's surface moves away from every other point. The space between them is actively growing. This is why we see galaxies receding from us in all directions, not because they are flying through space, but because the very space-time separating us is stretching. This expansion stretches everything within that fabric, including the very light traveling through it, causing the cosmological redshift that tells us the universe is growing. The creation of this flexible fabric from a state of infinite density is the ultimate origin story, one where the stage and the actors were born together in a single, unified moment, setting the geometric rules for the entire cosmic drama that would follow. This geometric fabric of space-time might not be as fundamental as it appears. Some of the most radical ideas in physics propose that our perception of a three-dimensional universe could be an illusion, a holographic projection from a two-dimensional surface. This is the holographic principle, a concept that emerges from the strange physics of black holes. When matter falls into a black hole, it seems to vanish, taking its information with it. This presents a paradox because quantum mechanics states that information can never be truly destroyed. To resolve this, physicists discovered that all the information about what falls into a black hole is not lost inside, but is somehow encoded on its event horizon, the point of no return. The surface area of the event horizon, not the volume inside, seems to hold the data. This led to a breathtaking leap. If the information for a three-dimensional black hole can live on its two-dimensional boundary, could the same be true for our entire universe? Could the cosmos we experience, with its vast depths and swirling galaxies, be a projection from a distant, two-dimensional surface? This is not suggesting the universe is a sci-fi hologram in the sense of a light show, but that the fundamental degrees of freedom, the true bits of information that make up reality, reside on a lower dimensional shell. The world we see and feel would be a rich and complex translation of that data. The mathematics of string theory provides a framework where this idea can be explored. In certain models, a universe with gravity like ours can be mathematically equivalent to a quantum field theory without gravity operating on its boundary. It is like a cosmic version of a DVD. The disk itself is two-dimensional, but it contains all the information needed to project a fully immersive, three-dimensional movie. In this analogy, we are not the audience watching the screen, we are the characters living inside the projection. What would this mean for our understanding of reality? It would fundamentally rewrite our conception of space. Depth, distance, and volume would be emergent properties, not primary ones. The universe would be pixelated at the tiniest possible scale, the Planck length, with a finite amount of information in any given region. This could even provide a path to unifying gravity with quantum mechanics, by describing gravity as a consequence of quantum entanglement on that lower dimensional surface. But is this just a mathematical curiosity, or could we ever test it? Scientists are looking for clues. One promising place is the cosmic microwave background. If the universe is a hologram, the patterns in this ancient light might show a specific kind of graininess or noise, a subtle limit to how much information can be stored in any patch of sky, imposed by the pixelated nature of the underlying code. Finding such a signature would be a revolution, proving that our tangible, three-dimensional world is a magnificent and incredibly detailed illusion, projected from the edge of space itself. That inflattened field, the cosmic engine driving the universe's explosive growth, could not maintain its furious pace forever. Its incredible power was rooted in a state of false vacuum, a high-energy configuration that was inherently unstable, like a ball perched precariously on the peak of a hill. For that fleeting fraction of a second, the field was stuck, and its pent-up energy drove the exponential expansion, but such a state was not meant to last. The field needed a way to roll down its energy hill to find its true, stable minimum. This transition, known as the graceful exit problem, is the moment inflation ended and the universe as we know it truly began. The process is thought to have been a cosmic phase transition, similar to water freezing into ice. In the supercooled state of inflation, the universe was uniform and filled with the high-energy inflattened field. But random quantum fluctuations eventually triggered a change. Bubbles of the new, stable phase began to nucleate spontaneously throughout the cosmos. Think of a pot of water just starting to boil. Tiny steam bubbles form at different points, then rapidly expand and merge until the entire pot is filled with boiling water. In the same way, these bubbles of true vacuum grew at nearly the speed of light, colliding and merging until the entire observable universe had transitioned to the lower energy state. As the inflattened field rolled down its energy hill in each of these bubbles, it did not simply vanish. It oscillated rapidly around its new minimum, and in doing so, it decayed. All of that immense potential energy which had been powering the expansion of space itself was dumped into the universe in a colossal burst. This energy transfer filled space with a hot, dense, and chaotic plasma of particles, a process physicists call reheating. In an instant, the cold, empty expanse of the inflating universe was flooded with matter and radiation, igniting the traditional hot Big Bang. The precise details of this decay are not just a technicality. They are written in the stars. The way the inflattened field oscillated and coupled to other particles determined the initial temperature and composition of that primordial plasma. More profoundly, the quantum fluctuations that were stretched to cosmic sizes during inflation were frozen into the fabric of reality as the reheating occurred. The specific spectrum of these ripples, their strength and distribution across different scales, was set during this graceful exit. This is why the patterns we observe in the cosmic microwave background are so crucial. They are a direct snapshot of the density variations moments after reheating. The slight hot and cold spots in that ancient light are the amplified echoes of the inflattened field's final moments. By studying their precise statistical properties, cosmologists can work backwards, testing different models of inflation to see which one's predicted graceful exit best matches the universe we actually observe. The end of inflation was not a failure, but a transformation. It was the moment the universe traded its potential for creation, exchanging the pure energy of expansion for the hot, messy reality of particles, forces, and a future filled with structure. That intricate cosmic web is the ultimate expression of gravity's patient work. If you could zoom out to see the universe on the largest scales, you would not see a random scattering of galaxies. Instead, you would witness a magnificent architecture, a vast network of brilliant galaxy clusters connected by long, shimmering filaments of starlight, all woven around incomprehensibly large, dark, and nearly empty voids. This is the cosmic web, the grandest pattern in all of existence, and its blueprints were drawn in the first instant of time. Its construction began with those faint quantum ripples, the gravitational seeds imprinted on the universe during inflation. After the release of the cosmic microwave background, dark matter, which had been waiting in the wings, took center stage. Unaffected by the pressure of radiation, it was the first to respond to the pull of these seeds. Slightly denser regions of dark matter began to pull in more dark matter from their surroundings. Over hundreds of millions of years, this slow, relentless gathering sculpted an invisible skeleton across the expanding cosmos. This dark matter scaffold formed first, a ghostly framework of dense knots connected by long, tendril-like filaments with vast, empty bubbles in between. This invisible skeleton then guided the ordinary matter, the hydrogen and helium gas. The gas, feeling the powerful gravity of the dark matter web, began to flow. It streamed along the dark matter filaments, a cosmic river system flowing toward the intersections, the nodes of the web. At these busy intersections, immense reservoirs of gas pooled, creating the perfect conditions for the birth of galaxy clusters, the largest gravitationally bound structures in the universe. Stunning supercomputer simulations show this process in breathtaking detail. They model the universe as a cloud of millions of particles governed only by gravity and the initial seed fluctuations. As the simulation runs, you do not see a uniform cloud. You watch as gravity pulls the particles into a delicate, web-like structure, a perfect match for the maps we create with our telescopes. You see the gas, represented in glowing colors, channeled along the invisible dark matter highways, crashing together at the nodes to ignite a firestorm of star formation. The galaxies we see are not scattered randomly. They trace out this underlying dark matter architecture, lining the filaments like diamonds on a necklace and congregating in massive clusters at the crossroads. The voids, those empty desert regions, are not truly empty, but they contain far fewer galaxies, making them some of the most barren places in the cosmos. This cosmic web is the final result of a 13.8 billion-year construction project, a project that began with quantum whispers and was built by the invisible hand of dark matter, all orchestrated by the unyielding force of gravity. Even our most cherished cosmic maps contain strange, unsettling features. One of the most famous is a peculiar alignment in the cosmic microwave background, dramatically nicknamed the axis of evil. This is not a malevolent force, but a mysterious pattern that seems to single out a specific direction in the cosmos. When scientists analyze the largest scale fluctuations in that ancient afterglow, they find that some of these hot and cold spots are not scattered randomly. Instead, they appear to be aligned along a particular axis, a kind of cosmic preferred direction that stretches across the sky. This discovery is deeply troubling because it directly challenges one of the foundational pillars of modern cosmology, the cosmological principle. This principle states that the universe on a large scale is homogeneous and isotropic. Homogeneous means matter is evenly distributed, and isotropic means the universe looks the same in every direction. There should be no special place and no special direction. The axis of evil, if real, suggests that on the grandest scales, the universe might have a discernible structure, a cosmic spine that breaks this perfect symmetry. So what could this be? The most conservative explanation is that it is simply a statistical fluke. When you have a vast amount of data, sometimes strange patterns emerge purely by chance. It is like finding a face in the clouds, a random arrangement that our pattern-seeking brains assign meaning to. Alternatively, it could be a subtle systematic error in our measurements. Perhaps our own solar system's motion through space, or even galactic dust, is creating a faint imprint that we have not fully accounted for, tricking us into seeing a pattern that is not truly cosmological. But the most thrilling possibility is that this is a real clue, a crack in our standard model pointing toward new physics. Perhaps our universe is not perfectly isotropic. Maybe it has a slight rotational preference, or its expansion is not perfectly uniform in all directions. Some theories even suggest it could be an imprint from a time before the Big Bang, a scar from a collision with another universe in the multiverse. The axis of evil remains an unsolved mystery, a quiet but persistent whisper in our most precise data, suggesting that the cosmos might be stranger and more structured than we ever believed. The universe's grand cities of light will not vanish all at once. Long after the great spiral galaxies have faded and drifted apart, a final generation of stars will keep a lonely vigil in the deepening dark. These are the red dwarfs, the smallest and most frugal of stars, and their lives will be measured in trillions of years, not billions. While massive stars live fast and die young in spectacular supernova, a typical red dwarf burns its hydrogen fuel with such slow, steady economy that its glow could outlast the current age of the universe 1,000 times over. Picture a single dim ember glowing with a deep crimson light, sipping its fuel so slowly that its future is almost eternal. But in this cosmos, nothing lasts forever. Even these patient sentinels will eventually exhaust their supply of hydrogen. The fusion processes in their cores will begin to sputter and falter. A red dwarf does not go out with a bang. Its end is a long, slow fade. Over eons, its faint light will dwindle, its red glow deepening toward the infrared until finally, it winks out entirely, leaving behind a cold, dark stellar corpse known as a white dwarf. This is the beginning of the degenerate era. The cosmos will become a vast graveyard populated by the fading remnants of a once brilliant age. The sky will be filled with the ghosts of stars. White dwarfs, the Earth-sized cores of suns like our own, will slowly cool from white-hot to black, becoming cold, crystallized spheres of carbon and oxygen, dark diamonds drifting in an endless night. Neutron stars, the ultra-dense leftovers of supernova explosions, will pulse their final, weakening beams of radiation into the void before falling silent. And black holes, the most mysterious relics of all, will loom in the darkness. For a time, this will be the final state of the universe, a static, frozen landscape where nothing new is born, and the only change is a gradual slide toward absolute cold. But even this is not the end of the story. Thanks to a strange quantum effect predicted by Stephen Hawking, black holes are not completely black. They slowly leak radiation, losing a tiny, almost imperceptible amount of mass over time. This is Hawking radiation. For a stellar mass black hole, the process is so slow that it would take longer than the current age of the universe to evaporate even a fraction of its mass. But given enough time, trillions upon trillions of years into the future, even the mightiest black holes will eventually evaporate. They will shrink, their emission of radiation increasing as they grow smaller, until in a final, faint pop of energy, they vanish completely. The degenerate era will give way to the final, dark epoch, a time when the universe is nothing but a dilute sea of subatomic particles and photons, expanding forever into an infinite and silent future. The death of the last star is not a single event, but the closing of a chapter that lasts for ages, a slow, quiet extinguishing of the last lights in the cosmos. These points of infinite density are a profound cry for help from our theories of physics. A singularity is not a place you can visit. It is a mathematical warning sign that general relativity, our most successful theory of gravity, has reached its breaking point. It tells us that at the very center of a black hole, and at the very first moment of the Big Bang, all the mass and energy of a system is crushed into a point of zero volume and infinite density. Infinite anything in physics is not a description, it is a declaration of ignorance. It means we are missing a crucial piece of the puzzle. The problem is that general relativity is a theory of the very large, the realm of planets, stars, and galaxies. It treats space and time as a smooth, continuous fabric. But to understand what happens at the heart of a singularity, we need a theory of the very small, the bizarre world of quantum mechanics, where probability reigns and nothing is smooth. These two pillars of modern physics are currently at war when it comes to these extreme conditions. To resolve this conflict, we need a theory of quantum gravity, a framework that can describe how gravity works at the subatomic level. Without it, the origin of our universe and the ultimate fate of anything falling into a black hole remain a complete mystery. Several promising candidates offer a way out of this conundrum. One is loop quantum gravity. This theory proposes that space itself is not infinitely divisible. Instead, it suggests the fabric of space-time is woven from tiny, finite loops, a kind of ultimate pixelation of reality at the smallest possible scale. This has a stunning consequence for singularities. In this view, there is no such thing as infinite density because matter cannot be compressed beyond the size of these fundamental space-time grains. The crushing collapse of a star into a black hole or the universe into a Big Bang would not end in a singularity. Instead, the immense gravitational squeeze would eventually meet a cosmic repulsion caused by the quantum nature of space itself. The collapse would halt and reverse like a ball bouncing. This is the concept of a quantum bounce. For a black hole, it raises the incredible possibility that the other side of the event horizon might not be a point of no return, but a gateway to a new, expanding universe. Our own Big Bang, then, might not have been the absolute beginning, but merely one bounce in an endless cycle of cosmic contraction and expansion. String theory offers another radical resolution. It replaces the idea of point-like particles with tiny, vibrating strings. At the high energies of a singularity, these strings would be stretched and excited, preventing the infinite densities predicted by classical physics. The singularity would be replaced by a fuzzy, energetic state often called a fuzzball, a tangled knot of fundamental strings that has a finite size and a complex structure. This would completely reshape our understanding of a black hole's interior, transforming it from a destructive pit into an object with a rich internal constitution. Whether through a bounce or a fuzzball, the true message is the same. Singularities are almost certainly not real. They are artifacts of our incomplete knowledge, placeholders for a deeper physics we have yet to fully uncover. Peering beyond them does not just tell us what happens inside a black hole, it offers our most tantalizing glimpse of what may have preceded our own universe, a cosmos that existed before our own time began. These invisible threads of force weave through the cosmos, connecting galaxies across the void. We find magnetic fields everywhere we look, from the swirling arms of spiral galaxies to the vast, empty spaces between galactic clusters. They are not simply passive features, they are active players, influencing how gas collapses to form stars, how cosmic rays are channeled across space, and how planets themselves come to be. But how does the universe, born from a non-magnetic fireball, generate these immense, organized fields? The leading answer lies in a powerful process called the dynamo effect. Imagine a simple bar magnet. Now, imagine that magnet is made of a swirling, electrically conductive fluid, like molten iron in the Earth's core or superheated plasma in a galaxy. As this fluid rotates and churns, it can stretch, twist, and amplify any tiny, pre-existing magnetic field, making it exponentially stronger. It is a cosmic feedback loop where the motion of the conductor reinforces the magnetic field, and the magnetic field in turn influences the motion. Our own planet's protective magnetic shield is generated this way, deep within its molten core. On a galactic scale, the entire disk of a spiral galaxy acts as a colossal dynamo. The slow, differential rotation of the galaxy, where the inner parts orbit faster than the outer parts, stretches a weak magnetic field, winding it up like a cosmic spool of thread and intensifying its power over hundreds of millions of years. This explains how the fields are sustained and amplified, but it leads to a deeper mystery. Every dynamo needs a seed. It requires a tiny, initial magnetic field to get started. Where did these first cosmic seeds come from? The dynamo theory cannot answer that. It is like having a recipe for turning a teaspoon of yeast into a whole loaf of bread, but having no idea where that original teaspoon came from. The quest for the origin of these seed fields takes us back to the universe's infancy. One possibility is that they were generated during the period of inflation. The incredibly rapid expansion of space-time itself could have created fundamental electromagnetic waves that froze into a faint, primordial magnetic field as the universe cooled. Another idea points to the violent phase transitions when the fundamental forces split apart. Think of the universe cooling like a pot of water, but as it cools, it undergoes a sudden shift like water freezing into ice. These cosmic shifts could have created turbulent bubbles and shocks in the primordial plasma, motions that might have generated the first magnetic seeds. There is even the chance that they were born from the chaotic motions of the first stars and supernova, their explosive winds seeding intergalactic space with faint magnetic fields that were later captured and amplified by newborn galaxies. Understanding this genesis is not just an academic exercise. Cosmic magnetic fields are the universe's silent architects. They help regulate the birth of stars by providing support against the collapse of giant gas clouds. They channel high-energy cosmic rays, and they leave their imprint on the light that travels to us across billions of light years. To build accurate models of how galaxies live and die, we must first understand the origin of the magnetic force that guides them, a faint whisper from the dawn of time that grew to shape the visible cosmos. These cosmic magnetic fields, and indeed all of physical reality, rely on a set of seemingly fixed numbers. But what if the rulebook itself is changing? The fundamental constants, like the fine structure constant that governs the strength of electromagnetism, are the bedrock of our physical laws. We assume they are immutable, locked in place since the dawn of time. Yet, a small group of scientists is asking a heretical question. Are these constants truly constant? To find out, we must turn the universe into a time machine. By observing the light from incredibly distant quasars, we can peer back billions of years. This light travels through ancient clouds of interstellar gas, which absorb specific wavelengths, leaving a unique fingerprint in the quasar spectrum. The positions of these absorption lines depend critically on the values of the fundamental constants, particularly the fine structure constant. If that constant had a slightly different value in the distant past, the absorption lines we see in these ancient clouds will be subtly shifted from their positions measured in laboratories on Earth. It is like finding an antique ruler where the inch mark is microscopically shorter than it is today. The measurements are achingly delicate, pushing our telescopes and spectrographs to their absolute limits. Some teams have reported tantalizing evidence that the fine structure constant might have been slightly smaller in the early universe, a shift of just a few parts in a million over billions of years. The evidence is not yet conclusive, but the possibility sends ripples through the foundations of physics. We have another, more local time capsule right here on Earth. In Gabon, Africa, lies the Oklo Natural Nuclear Reactor, a site where nearly 2 billion years ago, a rich vein of uranium ore and just the right geological conditions allowed for a self-sustaining nuclear fission reaction to occur naturally. Scientists have meticulously analyzed the radioactive waste products preserved at Oklo. The way these isotopes decayed is exquisitely sensitive to the constants of nature, especially the strength of the force that holds atomic nuclei together. The analysis suggests that these constants have not changed by any detectable amount in the last 2 billion years. This creates a fascinating puzzle. One method looking back over 10 billion years hints at a possible shift, while another looking back 2 billion years shows perfect stability. So what would it mean if the constants are, in fact, drifting? It would mean that our most cherished theories, like the standard model of particle physics, are incomplete. They are built on the assumption of fixed constants. If those constants are changing, even imperceptibly, it points to a deeper, more dynamic reality. One profound explanation involves the existence of extraspatial dimensions beyond the three we experience. In theories like string theory, the constants we measure might not be fundamental. They could be the result of how these extra dimensions are folded up, their geometry stabilized by fields. If those fields were slowly evolving over cosmic time, the constants would slowly evolve with them. Our entire universe would be a place where the very laws of physics are aging, maturing, or perhaps decaying. Finding a varying constant would be a direct window into this deeper layer of reality, a sign that what we call laws are merely temporary patterns in a much grander and more fluid cosmic tapestry. It would force us to rewrite our understanding of the universe, not just its contents, but its most fundamental operating principles. The smooth, predictable geometry of space-time is a cosmic mirage, a comforting illusion that shatters at the very smallest of scales. Dive down beyond the atom, beyond the nucleus, and even beyond the quarks themselves to a realm so tiny it defies visualization. This is the Planck length, a distance so minuscule that a single proton would be as vast as a galaxy in comparison. Here, at the very foundation of reality, the calm fabric of space-time dissolves into a state of pure, chaotic turbulence known as quantum foam. The trampoline-like sheet of general relativity is no longer smooth. It becomes a seething, bubbling brew where space and time themselves lose all definite meaning. Wormholes, tiny tunnels connecting distant points, flicker into existence for an instant before pinching shut. Pairs of virtual particles, one matter and one antimatter, spontaneously burst out of the nothingness, borrowing energy from the vacuum for a time so brief it cannot be measured. only to annihilate each other and return the lone. This is not empty space. This is a cauldron of creation and destruction, a frenetic dance of potential realities that underpins everything we perceive as solid and stable. Our entire universe, with its majestic galaxies and swirling nebulae, rests upon this frothing, uncertain foundation. To probe this quantum foam directly, to take a picture of this ultimate graininess of reality, we would need to concentrate an unimaginable amount of energy into a single point, a task far beyond any technology we can even conceive of building. It is the final frontier of the infinitesimally small, a turbulent ocean whose waves make up the serene-looking space-time we call home. A final, profound possibility redefines the very meaning of a beginning. What if our Big Bang was not a singular creation from nothing, but a rebirth, a phase transition from a prior cosmic epoch that has simply left its mark on our own? This is the radical proposal of cyclical universe models, which suggest that time and the cosmos itself may be eternal with no true start or finish. One of the most elegant of these is conformal cyclic cosmology, proposed by Roger Penrose. It posits that our universe's distant future and its infinitely distant past are mathematically the same state. In the far, far future, when the universe has expanded to near nothingness and only massless particles like photons remain, the concept of scale and distance loses all meaning. This smooth, empty, high-entropy state becomes identical to the smooth, empty, low-entropy state of a new Big Bang. Our universe is just one eon in an endless chain, with the final black hole evaporation of one eon seeding the initial conditions for the next through gravitational waves. Penrose even believes he has found evidence for this in circular patterns within the cosmic microwave background, potential imprints of colossal black hole collisions from the eon before our own. A different approach comes from string theory with the ekpyrotic model. Here, our three-dimensional universe exists on a membrane or brane floating in a higher dimensional space. A neighboring brane parallel to our own could periodically collide with ours. This collision would not be a violent crash of matter, but a transfer of immense kinetic energy into our brane, heating it to an incredible temperature and initiating the expansion we call the Big Bang. In this view, the Big Bang was a bounce, a moment of contact in an endless cyclic dance between cosmic membranes. These ideas are breathtaking, but are they testable? Scientists are searching for the ultimate fossil, a signal from before time zero. The most promising place to look is the primordial gravitational wave background. Just as the cosmic microwave background is the afterglow of the first light, this would be the afterglow of the first tremors in spacetime itself. Inflation should have created a specific spectrum of these waves. But a cyclical model, like the ekpyrotic scenario, predicts a dramatically different gravitational wave signature. Finding the wrong pattern could be the clue that our universe was born from a bounce, not a bang. Other potential clues lie in the detailed statistics of the cosmic microwave background or the large-scale distribution of galaxies, which might carry subtle scars from a pre-existing cosmic structure. The search for evidence of a pre-Big Bang universe is the ultimate archaeological dig, probing not into ancient rock, but into the very geometry of space-time and the faintest whispers of gravity, seeking an answer to the most fundamental question of all: did everything truly begin, or has it simply always been? The silence before the first stars holds secrets that might rewrite our entire cosmic story. To find evidence of a universe before our own, scientists are turning to the most subtle of messengers, gravitational waves. These are not waves of light or sound, but ripples in the very fabric of spacetime itself, vibrations created when massive objects accelerate. While we have detected waves from black hole mergers, the ultimate prize is the primordial gravitational wave background, the faint echo of the universe's violent birth. This signal would be a direct probe of the Big Bang's first moments, carrying information from an era when the cosmos was a seething quantum plasma. Different theories of the beginning predict different patterns in these waves. The standard inflationary model creates a specific, broad spectrum of these ripples, but a cyclical universe, one born from a bounce or a collision with another membrane, would generate a dramatically different signature. The gravitational waves from an ekpyrotic collision, for instance, would be far weaker and have a distinct frequency profile compared to those from inflation. Finding the wrong pattern would be a monumental discovery, a clue that our Big Bang was not the absolute beginning, but a transition from a prior state of existence. The challenge is that this primordial signal is incredibly faint, buried under a cacophony of other cosmic signals and drowned out by the louder gravitational waves from more recent astrophysical events. It is like trying to hear a whisper in a roaring hurricane. To detect it, we need observatories of almost unimaginable sensitivity. Next-generation projects are already on the drawing board. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, using lasers to measure the microscopic stretching of space as a gravitational wave passes by. In space, free from the seismic noise of Earth, LISA could be sensitive enough to listen for this cosmic hum. Even more ambitious concepts involve using the timing of distant, rapidly spinning neutron stars called pulsars as a galaxy-sized gravitational wave detector. By monitoring a network of these celestial metronomes across the Milky Way, astronomers hope to see the tiny, correlated shifts in their ticks caused by the long wavelength ripples of the primordial background. Alongside this hunt for gravitational waves, cosmologists are performing a forensic analysis of the cosmic microwave background, searching for statistical anomalies that defy the standard inflationary story. They are looking for specific, non-random patterns, like the concentric circles Roger Penrose believes are imprints of supermassive black hole collisions from a previous eon. They scrutinize the polarization of this ancient light, a property that can be twisted by the passage of gravitational waves in the early universe. Any deviation from the expected Gaussian randomness, any hint of a preferred direction or a strange correlation, could be a fossil from a pre-Big Bang era. The technical hurdles are immense, requiring ever more precise maps of the microwave sky and complex computer algorithms to sift through the data. Confirming or ruling out a cyclical cosmos is a primary goal for observatories now being built, like the Simons Observatory in Chile and its successors. The search is for a ghostly signal and a hidden pattern, a whisper from a time before time, that would tell us our universe is not a solitary creation, but one link in an infinite, eternal chain. From a single point of infinite potential to a cosmos of 1 trillion galaxies, the journey of our universe is the greatest story ever told. We have traced its epic from the first quantum whisper to the last fading star, yet the deepest mysteries only grow more profound. We are surrounded by ghosts, by dark matter that sculpts the galaxies and a dark energy that drives them apart, forces we cannot see but whose influence is written across the sky. We live by a set of physical laws so perfectly tuned that their origin remains an enigma, a cosmic rulebook whose first page is still missing. This is not a failure of science, but its very engine. Every unanswered question, from what banged in the Big Bang to what lies beyond the edge of our observable universe, is a beacon guiding us forward. Our quest to understand the cosmos is a testament to a simple, powerful truth, that we, a fleeting consciousness on a pale blue dot, can dare to unravel the universe's grandest secrets. We are small, but our curiosity is vast. It connects us to the very beginning and stretches toward the ultimate fate of all things. So tell me, which of these cosmic mysteries captures your imagination the most? Share your biggest question about the universe in the comments below. And if you are eager to continue this journey of discovery, subscribe for more deep dives into the wonders of space.